Hello, everyone, and welcome to this Nordic Tech webinar. The topic of today's presentation is the future of power management. Discover nPM1300. The presenter for today is Geir Kjosavik. He is the product director of power management here in Nordic Semiconductor. Then I'll just hand it over to you, Geir.
Thank you, Robin. I hope you can all hear me. Yeah, so before we start talking about the future of power management, let's just recap what is really power management. And power management is taking a power source, regulated or non-regulated, and distributing that power to the application. And in a lot of cases, we also distribute some of that power to a battery because it needs to be charged. And I understand as you design systems, the PMIC isn't kind of the center of your efforts a lot of times, but it has a very central function in the system. And I don't say that just because I'm a PMIC guy. It really has. And the fact that I view it sometimes as the boss of the system. It decides who gets power and who don't. And it decides what happens if, for example, the battery runs out of juice. But since it has this much power, no pun intended, it means that it can also do more than most PMICs do. And that is exactly what this PMIC that we're going to talk about today does. This PMIC, what it does is more than just the standard power management functions. This presentation will tell a story about that, and this story is not fantasy. This is very much real. The PMIC was launched last week, and you can buy evaluation kits, and you can order samples today. What's special here is that this PMIC packs more functions in one chip than any other PMIC of its class. And in our mind, in 2023, it's about time that somebody does this. You guys being product developers, you know that making successful products isn't getting any easier. The end customer is demanding more and more functions and more processing power and more kind of everything. And there's not much more. The space you have to put it in, or the volume you have to put all this functionality in, isn't getting any bigger. If anything, it's getting smaller. So if you look at all these typical PMIC functions on this list, if you're going to check off all of these, in a lot of cases, you will need to implement that using a lot of components. Or not. This PMIC does all of that. It supports all of those functions and a lot more. Now, we're going to go through all of these things further on. At a quick glance, it looks like any run-of-the-mill PMIC, but there's a lot more to it than meets the eye here. If we took a look at what it would require to implement all this functionality with an equivalent functionality with components from one of our competitors, a competitor that has a much bigger PMIC portfolio than we have. And we're kind of surprised to see that you actually need a total of 8 chips and a bunch of extra components to do that. So getting all of this functionality into one PMIC, as we've done, it wasn't easy, but it isn't rocket science either. You just have to have the imagination to do it. What this means to you is obviously a simpler circuit. You have one chip and some passive components versus 8 chips and a bunch more passive components. But it's more than just the complexity of the system. It also the complexity of how you interact with the PMIC, how you configure it, how you evaluate it. We've created, and we're going to show you some details of that, a piece of software that actually makes it possible to access the PMIC and get it up and running without writing any code. And that is partially also true with our competitors, but here you have to read also the data sheet. And in our case, to just get it up and running, you don't even need to do that. So that's an ease of use thing, and ease of use can be considered a convenience factor, because when everything is in production, who remember what it would take to get the things up running in the first place. But what isn't a convenience factor is physical size. When every cubic millimeter counts, that circuit on the right that does the same thing as the circuit on the left isn't all that appealing. And actually, I take that back. The circuit on the right doesn't do all of the things that are in the left. There were some functions in the nPM1300 that our apps guy didn't really know how to do. The power failure warning being one of those, for example. We had an early customer who also tried to do this outside of the PMIC, and he was so happy to see how much better this function works when it is implemented where it belongs on the PMIC itself. So that's kind of the teaser. That is all the bragging and the big words, and now we're going to unpack some of this and look more into the details. So if we start with the power management functions, you find the usual suspects on the list: buck converters, load switches, battery charger, all these kind of things. Except I would argue the fuel gauge. It's rare that you find a fuel gauge function on a PMIC of this size. And since it is such an essential function and it carries so much value all the way through to the end customer who wants to know how much juice he has left in his battery, we're going to give it a whole section later on in this presentation. Now, on the system management side, there are some pretty common things. There's some quite rare things. And there are a few things here that are making history because we're bringing out the first PMIC to have them. So we're not going to, we're going to go quickly through some of these and then focus on the most interesting ones in my mind. So let's start with failed boot recovery. Now, in a perfect world, software never hangs. Systems always boot. And in a semi-perfect world, software can hang sometimes, but always hangs after the watchdog has been initialized. But in the real world, even that can happen. So in the case that the software goes off in the weeds or somewhere else where it shouldn't be before it has managed to initialize the watchdog, what this PMIC does, if this function is enabled, is that it waits for a while for the host to signal that, hey, I'm up and running, I booted, okay, everything's fine. If it doesn't get that within a certain time, it power cycles the whole system to give it another chance to boot up. Now, if it's a really, really bad error, that it will just keep rebooting. But we all know that something that goes wrong in one boot goes okay in the next one. And it at least gives you a chance. Hard reset. This is a function that most of us have in one of our gadgets. Again, in this non-ideal world where software goes off to do things that it shouldn't, we sometimes have to, and even if the watchdog timer is enabled, we have to intervene and get the whole thing fired up again. And for devices where you cannot take the battery out and restart it that way, the manufacturers usually put in a hard reset function where one or a combination of two buttons has to be pressed for a time power cycle the device. That there are chips that do that for you, but there's no reason to buy those because we think because you can build that into the PMIC. It's where it really belongs, and that's where we put it. Hibernate. Hibernate is, for those who know what chip mode is, a very, very low power state where some circuitry inside the PMIC is the only thing that's running. Hibernate mode is the same thing, except now that you have a timer running that can wake the system up. So let's say the system knows that there's nothing I need to do until Saturday morning. So it kills its own power. The whole system powers down except for some important parts of the PMIC, some essential parts of the PMIC and a timer. And then that timer will wake the system up at on Saturday morning and get it running, or until somebody pushes a button. Watchdog timer. A lot of PMICs have this, but and it's important. I would say every PMIC should have this for one reason. If you are overriding the automatic charge control, let's say that you increase the charge current to what the automatic charging would give you, then what happens is that if your software crashes, the PMIC will be left charging at a much higher current maybe than it should. And then when something happens, there's no mechanism there that can take care of it because it has been overridden by software. And that's really bad if the software crashes. So there should always be a watchdog on the PMIC that stops charging if the PMIC understands that the host software is unresponsive. Now we've taken that, and some PMICs have this, but we've taken it even further. Obviously, we implemented also the ability for this watchdog to reset the host. But as the first PMIC in the world, we've also given it a secondary function where upon timing out, it can power cycle the entire system. So that's kind of a choice that you can make. The last thing is the power loss warning. And this is one use case where I can imagine this being used is, for example, if you reflash a device and despite giving the user warnings that the device should be on a charger, you should not be turning it off or anything, it still loses power. So what the power loss warning does, it's a dedicated interrupt line into the host. And when it fires, it will tell the host that you just lost power. And that could be because the battery ran out of juice. In the case of a removable battery, somebody opened the battery door and took the battery out. Or it could be a depleted battery on charging and somebody just unplugging the charge cable before the battery has reached a state of charge where it can power the system. So power is just lost. And this warning then goes into, if you design it right, then goes into a high priority interrupt at the host and tells the host that you just lost power. Now, whatever energy is left in your deep coupling capacitor is what you have left to run on before the brownout detector gets you. And hopefully then you design the size of this capacitor so that it has some time to get going or to keep going before it gets stumped. So with all this stuff, there's a lot of configuration and status registers hooked to the end of that I2C bus going into the PMIC. And we could have left you with the data sheet and have you burn the midnight oil pouring over the register file details. In the data sheet, the register file description takes up quite a bit. But we're not that kind of company. We think that's unfair. We really want this to be a good out-of-the-box experience and a good design experience. So what we've done is that we've designed a piece and a PC application that makes life a lot easier. And that's the npm Power Up app, which is a part of our NRF Connect for desktop infrastructure, for those who knows that's part of that ecosystem. And let's talk about how we make life easier that way. In again, a perfect world, things are easy, and we recognize that we don't live in that. We live in a world where the hardware designers don't like to spend time writing code, and most software engineers don't like spending time reading data sheets. Yeah, I know I'm generalizing right now, but I think we can agree on that kind of a common theme. And in this perfect world, they wouldn't have to, and our tools try to create that perfect world for them. Because with the npm Power Up, you don't have to do that. To get the PMIC up and running, you use an intuitive user interface on a PC that's connected to our evaluation kit. And without writing a single code, or not even looking at a long register file description, you can have the PMIC do stuff within a minute after everything is up running. You can enable a buck converter, you can set it to a certain voltage, you can change the charge current, you can enable charging, disable charging, do a lot of things. And when you get acquainted with the PMIC and you've found the configuration that you want to use in your application, you press a button and npm Power Up exports all that code over to the software guy who implements this in the application code. So really, really easy. You're gonna love this. But we got to talk about the fuel gauge, because that's where it really gets interesting and unique. Yeah, so if you like what you've seen so far, now it's only going to get better. The fuel gauge solution in the nPM1300 is like nothing you've ever seen before. It is a fuel gauge solution that is as accurate as a hardware solution, a Coulomb counter, or some of those other solutions that exist. But it has the power consumption and the simplicity of a simple battery voltage measurement, and requires exactly 0 external components. and on the topic of battery voltage measurement, we know that's the quick and easy way to generate some kind of fuel gauging in a device. You measure the battery voltage and you determine the state of charge from a lookup table. It's simple, it's inexpensive, it kind of works, but when you take a look at it, it is grossly inaccurate, especially at varying temperatures. But even at room temperatures, in my mind, it is pretty bad. So we have taken a look at that. We have a really expensive instrument that has a super accurate Coulomb counter at a power consumption and a cost that is out of reach for most embedded systems. But we use that as a reference. And we ran the nPM1300 fuel gauge with that in parallel with that Coulomb counter reference, and also did the traditional simple voltage-based lookup table approach. And what we found is pretty interesting. So here, as we discharge the battery over 10 hours time, using a pulsing pattern that's usually really hard for, makes it even harder to use the voltage-based lookup. They work much better when you have a really solid, steady power draw from the battery. But in, for example, a Bluetooth speaker, that's not what you have. It's very spiky and very dynamic. So that's what we did. We subjected the battery to that kind of power curve or power profile. And what we found is that the voltage-based lookup, not only is it inaccurate here at the beginning, it varies between being reasonably accurate and deviating 20%, is that this pulsing messes up the terminal voltage of the battery. Even if you read the OCD voltage, there's a little bit of lag and a little bit of memory in it. So it keeps jumping all over the place, and that's the width of this gray band. And so here is the difference in state of charge, and here's the absolute difference. So it is 20% off at the worst, and then it goes down to being only 10% off at the worst towards the end. But remember, this is at room temperature. We start with a battery that's about 25 degrees and ends up at 25 and a half degrees, ends up at 23 and a half degrees. So it drops 2 degrees centigrades over the course of those 10 hours. So no big temperature swing by any definition of the word. But so it's still pretty bad. But what happens when we bring this into a environment with varying temperatures, it gets absolutely horrible, and in my mind, almost unusable. Here we vary the temperature from minus 5 degrees centigrades to plus 50 degrees centigrades. So huge swing. Probably more than most consumer applications, at least, will usually see, but we do this just to make a point. And where it really is difficult for both of these solutions is where we rapidly increase the temperature from minus 5, or actually minus 10 degrees centigrade is what we have, to plus 40. So that's like a good Norwegian winter, and then going to a spring day in Arizona in about 20 minutes. And we see that the nPM1300 fuel gauge struggles a little bit. It deviates by 4%, and that's the maximum deviation over this whole 4% from the reference over the whole discharge. But the voltage-based approach differs between being 10 and 30% off. And the poor consumer who see this drop in state of charge that recovers quickly when this temperature is rising is going to be confused. Do I need to charge soon, or what's going on? And if this happened towards the end here, maybe the application would say that, no, you're out of juice, when you're not. So this just, there's no way to create any confidence in the state of charge estimate on the end user side when you are this inaccurate with your data. So this almost sounds like fantasy, but it isn't. And I'm going to show you how we did this. The clue here is the fact that we're utilizing the almost unlimited processing power of the host SoC. When you have a Cortex M33 clocking away at many megahertz, you have a lot of processing power that you could utilize without the application code almost even noticing. So we do have the host do the heavy lifting here. The only thing we do is we give it access to some vital parameters of the battery. We have a non-intrusive current monitor that measures the current flowing into and out of the battery. We have a voltage divider that gives access to a measurement of the battery terminal voltage, and the thermistor that we're already measuring for the GITA compliance. We also have the data. So we have 3 data points: current, voltage, and temperature. And if then the SoC or the host has enough information about the battery that's connected, it uses a sophisticated algorithm that we've developed to accurately determine the state of charge. And for some reason, then this is where it really becomes, I don't know how this really works, but we just have to accept the fact that it does, because I don't understand all the math that was put in here. The beauty about this is that you don't have to measure these three parameters very often at a very high frequency. Once per second is okay, and the algorithm is only a few, not that many kilobytes, so it takes about an extra. We implemented this in a gaming mouse, so we tried it out just to check out some different load profiles, and what we found is that it used about four microamps with a 1 second, 4 extra microamps during with a 1 second measurement interval. But you only need to do that with when the host is actually running code. If the host is asleep, it doesn't need to wake up every second and measure this, because that would just totally kill the power down current consumption. If it's asleep, and no matter for how long, and no matter what happens with the battery in the meantime, whether it's just sits there and slowly gets discharged, or it actually gets charged while the SoC is sleeping, it doesn't matter. When it wakes up, it will read these three values again, compare them to what happened just before it went to sleep, and will accurately determine how much the state of charge has changed while it was asleep. So the excess power consumption here only applies when the host is up and running anyway. So how can you use this? As I said, for this to be accurate, the fuel gauge needs to know some vital parameters of the battery. And these you cannot just read out of the data sheet. The host actually has to learn these. But it only has to learn them once, and it only has to learn them from one battery. At least if you're using different battery models, obviously you have to do it multiple times. But if you have one battery model, we found that the parameters that we characterize are really consistent through production. So you get away with doing this once. And here again, our PC application, npm power up, comes in. Because not only does the npm power up give you access to everything inside the PMIC, it can also do this battery profiling for you. And most applications out there from competitors require some kind of battery profiling to be accurate. And some of them require you to send the battery to them for them to characterize it and give you the model back. We don't have to do that. We have a PC application that can do this. We have an evaluation kit that is a part of this. And when you connect the evaluation kit to a special fuel gauge board that provides the right resistive loads for this process, you can do this in your own lab. And the way you do it, you take the battery, connect it to the EK, connect that again to the fuel gauge board, you press a button, and you walk away, and you come back, I think, 24 or 48 hours later, and you have 1/3 of the profile. You repeat that twice more with different temperatures. You run it a total of 3 times at 3 different temperatures. And when you've done that, you've built a model that gets exported with the rest of the configuration code, and then linked in with the application codes. And now the nPM1300, together with your SoC application host, has together work out a perfect fuel gauge that very accurately determines the state of charge of the battery. So and that extra, except for just finding a temperature chamber and hooking everything up, as I said, you press a button and you walk away. It's pretty much autonomous. So I hope that was that looked interesting, and we're getting towards the end of the presentation here, and we'll wrap it up with a summary before we go into the Q&A. So the nPM1300 is a PMIC with the functions that you expect to find on a PMIC, plus some unique system management features. Now, there are still PMIC functions there that aren't implemented. We couldn't do it all. That would not be a non-viable product and not be cost competitive. So there's stuff that's going to come out on Nordic PMICs going forward that will make them even more complete than the one we have. But we're going to build on this philosophy of putting in unique system management features. The way to evaluate and develop on this PMIC is really easy because we do have a PC app, npm Power Up, that has everything you need. You have access to absolutely every knob and dial inside that PMIC through that software. And you will be able to export whatever configuration of every single thing in there through the process of software export, and then the drivers under the correct configuration being implemented through our software development kit on the software side. And we'll say this is the ideal companion to our Nordic SoCs and SIPs. This can work both with our cellular product and with our Bluetooth products. And what you now get with using a PMIC from Nordic together with a radio RF chip from Nordic is a system where you have Nordic provides full control over the entire energy path from the battery to the antenna. From when the electrons leave the battery until that energy is transformed into RF signals that eventually end up as electromagnetic radio waves, we help you take care of that energy path all the way to make sure that the battery life is as long as possible. And at the same time, we give you a bunch of features that help you build products with all these things that your customers are asking for, including an accurate estimate of when their battery, how the battery is doing. So with that, Robin, I think I'm done, and I hope there are some good questions in the chat.
Yeah, we'll answer some questions now. I'll start with one about the nRF91 series. So what is the recommended configuration when you use this PMIC with a 91 series SIP? Should the PMIC only charge the battery, or should the nRF91 be connected to the regulated outputs?
That's a good question. And I didn't really go into the details on the regulated rails, but the buck converters in this they can support up to 200 milliamps, and the 9160 consumes about 500 peaks. So that's not going to work, and nor is it necessary, because the nRF9160 has a really good PMIC built into that SIP. So all you need to do is to hook the nRF9160 up to VSYS, which is the unregulated rail from the nPM1300, and then you can use those bucks for other things in the application should you have that. So that's really easy.
Okay, then there's one wondering about the GPIO. Is it possible to implement a push button on-off controller using the GPIO's /hibernate/ship mode such that a single button can turn a power on to the device when it's pressed and then off again when it's the same button it's held for longer, which is common in notebooks and such these days.
Yeah. Okay. So yes, but there's no automated functions. You would need a little bit of help from the SoC. And this is not the first customer to ask this, and this is why we're going to implement this as a fully autonomous function in the npm 1300's bigger brother when it comes out sometime next year. But so the way you have to do it is so that the button that you use to bring it out of ship mode, that would be the one that you wake it up from hibernate mode or from ship mode, and you can do that. So what you do is that you hook that button also to one of the GPIOs, and you have that GPIO generate, or you could also connect it directly to an interrupt line on the host, or you could have the PMIC generate that interrupt, so that when that button is pressed and the system is on, the SoC sees it, and if it's hold down for enough time, it registers that, and then it powers the PMIC off and powers itself up. And now this goes into ship/hibernate mode, and the same button can bring it back out. So for the turning on, the function is there. The turning off, you need a little bit of assistance from the host to register that the button was pressed and time the duration of the press.
Great. Then we have a shorter one, or actually two short ones. What is the battery chemistries that's supported by this PMIC? And there's another one also asking about the voltages.
Yeah, that's a really good question. So it's lithium ion, lithium polymer, up to 4.45 volt termination voltage, but also LiFePO4 at 3.5 volt, I think, termination voltage are supported. But the online datasheet will explain these, and if you have a battery chemistry that's unmentioned, just take a look at the cutoff voltage on the low side and the range of the termination voltage on the high side, and determine if that works with the charge profile of the battery that you intend to use. But there's quite a bit of programmability in the charge termination voltage. So we try to capture almost all lithium chemistries out there, but there are some weird ones that we aren't supporting.
Then there's a question about, in a system with limited I/O capabilities, is there a hardware configuration for the nPM1300, or is the two-wire interface the only possible way to configure it?
There is a hardware configuration, but it is very limited, and if you're charging, even to enable the charger, you would need a host to do it. The only things that are hardwired is which buck converter should start up, and one or the other one or both, and at what voltages. That is determined by resistors that are strapped between two pins and ground. And I think if you don't have a battery, you just go from DC voltage between 4.5 and 5.5 volts. In theory, you could make it work, but there's so much stuff in there, and most of it you will need the I2C bus to work with. If you want to use a much simpler PMIC that has a layout time configuration only, you should look at the smaller nPM1300. That one doesn't even have an I2C interface and is totally configured with resistors and pins strapped high or low.
Then we have a very specific question. Can the event VBus removed be used to turn off the device to implement a charge-only mode like modern smartphones, i.e. still boot into a minimal application that just drives the display to show the current charge?
Oh, that is a good question and a complicated one. As I can see somewhere where that is going and envision some of that user interface, but I think that is something that's beyond what I can resolve in a webinar Q&A. So because I preferably have some visual cues as to what we're trying to do here. So I recommend you send that question to our support people, and they will hook you up with the expertise that can answer the question.
Yeah, devzone.nordicsemi.com.
That's the one.
Why do we have to use the SoC to perform the algorithm calculations for the fuel gauge? Why can't you put that on the PMIC is one question.
Oh, we could put that on the PMIC. Absolutely. And we've seen people do that. The problem with that is the PMIC doesn't have any form of CPU or memory. So that would have to be implemented as logic calculations in gate logic, and would be totally inflexible and would increase the cost of the device quite a bit. And with inflexibility, we're working on and refining this all the time. This fuel gauge that I showed you now may be much better next year because we've figured out something smart that we haven't thought of. So there is, the only advantage of that is, yes, you will have a totally autonomous, isolated fuel gauge, but it would be less flexible, more expensive. Absolutely. Yeah, so that's just it is the most economical way to do it. That is why and most flexible way to do it. That's why we've done it.
Speaking of cost, do we have a ballpark cost for this IC?
Yeah, but I would encourage you to go to your distributor or Nordic sales representative and get a quote. So I wouldn't feel comfortable giving any pricing information in this kind of form.
Very good. What is the maximum input voltage supported by the battery charger?
5.5 volts for charging. It will stop charging if it gets above that, but it has an over voltage protection, so it can tolerate a voltage of up to 22 volts coming in. And that is important because if you build a system with a USB-C charger and somebody pulls the plug, the USB-C plug out of their laptop and sticks it right into whatever you've built, then there could easily be up to 22 volts of residual charge sitting on that. So in order to make sure the PV can withstand that, we've designed it with an over voltage protection up to 22 volts, but it will not charge above 5.5. If you have if you have 6 volts coming in, you have to burn off half a volt somewhere.
How do I combine this with a small solar panel?
That is, it's not built to do that, and it depends a lot on the number of your cell configuration. If you had the right number of cells in series, you could get, and you have a consistent irradiance, you can get to a point where you may be able to use the USB input. But we have on our roadmap stuff that will do that much better. I can't reveal any details, but that's just stay tuned to see more PMICs coming out from Nordic and see if we can find something that solves that for you. This one isn't. There may be some corner cases where it could be used and made to work, but it's not ideal, and in most cases it won't work because it isn't designed for that use case.
Then we have one more about the purchasing of this device. When will distributors, for example, DigiKey, start offering the nPM1300 as an IC, a freestanding
That
of the kit?
they will do in October this year when we release it to mass production. But now you can now order samples through the Nordic sample ordering system.
Then there's a question about the PMIC initialization through I2C. If they are always the same at startup, is it possible to store it in some memory so it can reload automatically?
There are, yeah. So the register file is divided into two. There's a totally volatile part and one we call a sticky part. It's not non-volatile because if you lose battery power, then everything goes. But when the system is powered up, meaning that the buck converters are going live from a powered down state, most of the registers are cleared. But there are some sticky registers, as we call them, some essential functions. For example, the enablement of the boot recovery from failed boot. That one stays on even if the device power cycles the system. And there's also a few scratch context registers in there that you can write so that when you wake up from a power on cycle, you can read those registers and find a history for what happened. But I mean, essentially making your own semaphore code, you can read that scratch register that's a part of the sticky section of the register file and determine where you're coming from, what happened prior to getting your power cut off. So that's the answer to that. The datasheet will provide a lot more accurate detail there than I can do from memory in a Q&A session.
Then there's a question if this could be used with wireless charging.
Yeah, you can. Depends on how you want to do it. But if you can take that wireless charging coil, whatever's coming out of it, and provide a 4.5 to 5.5 voltage going into the V-bus pin, then the PMIC wouldn't treat that any differently than the same voltages coming from a USB cable. So yeah, just need to develop that front end to make that happen.
And then there's a question, what is the key delta between the nPM1100 and the nPM1300?
The what delta?
And I'm assuming they mean the key differences.
Oh, the key differences. Okay, the key differences are many. Two buck inverters instead of one. They're 200 milliamps instead of the 150 milliamp. It has load switches. It has LDOs, GPIO, digital configurability, all these system management features that I talked about. The 1100 do not have that. The only thing that are in common is, and it can also charge twice the charging current. So the nPM1100 I would regard as a very, very small superset of the nPM1300.
Then we have another question about the fuel gauge. and charger. It's multi-chemistry capable, but does that include primary cells?
That's a good question. No, it does not. You could ideally run this from a primary cell battery if providing that the battery cell or the battery voltage was within the range that this is designed for rechargeable batteries. But and then you had to disable the charger to make sure you didn't attempt to charge the battery. But the fuel gauge wouldn't work because there's no way you can't use this profiling scheme to profile a primary cell battery. But we have in the works a PMIC that will do this, that is specifically designed for primary cell batteries, with both a fuel gauge and also mechanisms that will make, for example, a weak coin cell battery last much longer. So stay tuned. I think a little less than a year from now, 9 to 12 months from now, we'll be revealing the details on that one. And that is a very interesting device that is specifically made for primary cell batteries. The amount of primary cell batteries that could work with this one is really limited, and the fuel gauge would not work at all. It's designed for rechargeable batteries only.
Then there's a question about the power loss warning. Does this communicate over the I2C bus, or is there a separate interrupt line?
It is a separate interrupt line. Yes, that's a valid question. I2C would be too slow. Before you even begin to read up and understand what's going on, you would have lost power and you'd be dead. So that is a dedicated line. Whether it's a dedicated pin or whether you set one of the GPIOs to have that function, that I don't remember, but it's a hardwired signal that goes wherever you want it, preferably to some low latency, high priority interrupt line on the host, so that a host gets the message immediately without having to without having to read anything from the PMIC. And also, if you have circuitry on the board that really should be shut off, and because they don't appreciate the decaying voltage that you experience when all the decoupling capacitors on the board just bleed out as they lose power. If you want that to be cut off immediately, you can also hardwire that signal to cut things out before you start seeing VCC drop. But it is made to give the host the message as quickly as possible, so that it can take action while it still has some energy to utilize.
Okay, then there's a question: if there's any way to get a 5-volt output from the NPM? The bucks only go up to 3.3.
Yep, that is a valid question, and to do that, you would need a boost or a buck boost converter, and this one doesn't have that. And the way you solve that is that you use some of the money and some of the board space that you save with all this integration, and you find a standalone discrete buck or buck boost controller that can do this for you, and you use that to pump it up to 5 volts. That's the only solution. We're going to have this solved on PMICs further on the roadmap, but this one can only convert down, unfortunately. So that would be the solution.
There's one saying, great presentation. Could this be used with a 12-volt input?
Unfortunately, no. Then you would need some way to bring that 12 volts down to between 4.5 and 5.5. And that, again, if you could find we're again adding one more component, a buck converter, a discrete buck converter that can do that, then you're good. But that would have to be the solution. If you hook it up directly to 12 volts, you will not destroy the device, but it will not do anything because it stops. It cuts off once it reaches 5.5 volts.
Then there's a question if the fuel gauge algorithm, how does it cope with battery aging?
Oh, it's a very good question. So battery aging is, and we're in the middle of testing this right now, because as you understand, this is difficult. You first have to age a battery, and then, or multiple batteries, and then test it. So in theory, it should be able to cope with this, because what happens is that with an aging battery, you will, an old battery is very much like a cold battery. It has less capacity and has higher internal resistance. So we're working on characterizing how if the mechanisms built in here really handle that well, and if they don't, we'll have to adjust them and maybe spin another version. So exactly how well that works, we assume that it's going to tackle it really well, but we're in the midst of finding that out right now. So stay tuned. But it's an extremely good question, because that is the problem, and we all remember an old cell phone that you take out on skiing, for example, and the state of charge drops from 90% to 5%, and just stays at 5% for hours while they're skiing. And this is obviously because the fuel gauge isn't handling this good well enough. So that is, our intention is that it should, and we know how to do it. We just need to make sure that it does, and if it does, make the necessary adjustments.
Okay, then we're on to the couple final questions. Does this PMIC work with batteries that don't have an internal temperature sensor?
Yes, they do. We would, though, recommend that you put a temperature sensor somewhere. Well, that's entirely up to you. But yeah, the data sheet should be really clear on what you do if you don't, if there's nothing to connect that NTC input to. So it will.
How can I get samples of nPM1300 for testing and using it in my projects?
That you can order through the Nordic sample order system, and then you can buy the evaluation kit from any of our distribution partners. They're in stock with DigiKey, Mouse, or everybody that we go, all our distribution partners.
Then we have what is the power consumption of the estimation algorithm on the fuel gauge?
Yes, that's a very good question. We have an app note coming out hopefully this week that will detail that. It depends on a few things. First of all, what frequency you're running your host processor at. And I think that is one factor, but also how often you sample. And if you have a very dynamic power consumption with a lot of spikes, you may want to sample quite often. I don't now remember what the typical intervals are. And if not, if it's more stable, you can sample at a lower frequency. But the only power consumptions is the processing power needed to run those calculations. So it's very little. I think we're talking a few microamps, and more importantly, it's only when the processor is actively running. When it is asleep, you don't have to do these measurements. But look for that application note when it comes out, and it will detail those numbers.
Okay, then there's someone who's wondering, does the PMIC have a supervisor that cuts power when the battery voltage is below a certain threshold? Or do we need an additional component to handle that?
Yes, it does. I don't remember now from the top of my head what that voltage is, but it's a fixed voltage where it cuts the battery, unless the battery has done it already, because batteries also have under voltage protection put in.
Yeah, it's safe to, or I can mention that the nPM1300 is not meant to be used with raw battery cells, right?
Exactly. In that case, you do that on your own risk, but I would really recommend that you then add some additional circuitry. So it's intended for use with batteries that have this yellow tab on the encapsulation, which means that they have short circuit protection, under voltage and over voltage protection built in.
Okay, then we have a question about the power loss warning. How does
Yes.
the power loss warning propagate to the host device? Is
Yeah,
there a
I
separate
should
interrupt line?
have mentioned that, shouldn't I? It is a dedicated line that you can hook to an interrupt on the host processor. So there's no, obviously no I2C I2C command, because that would too long to take. So I think when you use it, you configure one of the 5 I/O pins or GPIO pins to be that signal that you feed into whatever high priority interrupt input you have on your host. That's
Okay, then there's
a dedicated signal.
Yeah, very good. Then there's a question about explaining the fuel battery gauging, the fuel gauging. I think we already explained it, so I'll just jump to the next. And there's also a short one about, does the fuel gauge also consider current use?
Yeah, I'm not sure if I understand that question, but it does measure the current flowing into and out of the battery, and it uses that parameter together with the battery temperature and the battery voltage to determine the state of charge.
Then we have an interesting one. Is the fuel gauge usable for a coin cell?
No, it is not. The fuel gauge is usable only for rechargeable batteries, and this PMIC is made primarily for rechargeable batteries. Now, obviously, if you have a primary cell battery that operates within the voltage range that this device is determined for, yes, you could use it to power the device, but that fuel gauge algorithm doesn't work for that. Having said that, we have in design a PMIC for primary cell batteries that will have that fuel gauge. So I think, around sometimes about 9 months from now, we'll have some exciting news. 9 to 12 months from now, have some exciting news on that and show it. And that is a primary cell PMIC that not only gives you a fuel gauge, but also makes your battery last, your coin cell last longer than any other PMIC.
Then there's someone asking about what's the fuel gauge doing differently from other fuel gauge solutions. I think we answered that. Maybe they're poking around for some.
Recap quickly. So other fuel gauge solutions depend on some dedicated hardware to do this. Either you need to use a separate chip. That is the most common way to do it. Here, the whole thing is built into the PMIC, and we can do that because the hardware associated with this is almost nothing. It's such a small part of the PMIC that because we're relying on the processing power of the SoC to do the heavy lifting. So sometimes Coulomb counters and other ways of estimating state of charge comes built into the PMIC, but these are functions that are complex and add to the cost of the device. So the beauty about this thing is from a hardware perspective, it costs nothing because most of the work is done in software. That's the main the main difference.
Then there's someone wondering, or they are assuming that this PMIC also works for batteries without a temperature sensor.
Yes, they do.
Could you feed the PMIC temperature from a different source, for instance, inside the device?
Yes, if you connect a thermistor that is if you connect a thermistor that is about the same characteristics as of those typically found in a rechargeable battery pack, you could stick that on top of the battery or somewhere else. But I strongly recommend that you measure the battery temperature either by using an internal thermistor or one physically attached to the package with a good thermal connection, because it is important. We also have in this device the full GEITA compliance, which means that at very low temperatures and very high temperatures, the battery charge current is reduced to protect the battery. This is also configurable. Both the current reduction and the temperature limits are adjustable, but without having a thermistor that directly measures the temperature of the battery, then you may be missing out on that protection. A little bit of depending on how large your device is and how easy the whatever area or you measure correlates to the battery temperature.
Thank you. Then there's someone wondering if it's compatible with lithium metal batteries. I'm assuming they mean the lithium ferrous oxide.
Yes, the lithium ferrite oxide batteries or LiFePO4 are compatible. The data sheet explains which ones, but what I suggest is that you'll look at the charging voltage range, so the cutoff voltage, and the upper range, which is adjustable, I think between 3.5 and 4.45, and make sure that that fits the battery that you intend to use. There are so many different battery chemistries out there with a wide variety of termination voltage, cutoff voltage, operating voltage. So I encourage you to just look at the discharge curve and the typical operating characteristics of your battery, and you compare that with the range of battery voltage that we can handle in the device.
Then there's more people eager to start designing. How is the maturity and availability of the product? When can we start the design in process?
You can start designing it now. We are looking at a volume production for this in October, but the device is being fully validated, and you have the evaluation kits that you can buy now with the chip on them, and start designing right away. Software drivers for most of the functions exist. There are a few of the odd ones that we don't have in our software development kit. They exist as bare metal drivers, but we can help out with that. But everything is there, so there's nothing stopping you from designing right away. Datasheet is on the web, and everything you need.
Then there's someone wondering, what happens to the buck output when the battery voltage drops below the selected output of the buck?
Yes, that is a good question. So it actually, things start happening before it drops there, because the buck needs a little overhead, like I think it's 300 millivolts or something, to operate. So the voltage feeding into the buck needs to be higher than the buck output. How much higher depends on how much current you're drawing. The higher current you're drawing, the higher that margin needs to be. But the data sheet explains all of that, and that is just a deficiency of buck converters, and nobody in the world, I think, has found a way to design around that. You will not go up. You will not be able to convert to the same voltage as the voltage coming in. What's happening is that as that margin decreases, because the battery voltage comes down, and you start getting into a territory where the buck struggles to regulate, you will first see an increased ripple on the output current, because the buck isn't working properly, doesn't have enough voltage to work with. And you will see an increased ripple, you will see a decrease in efficiency. And as you start dropping the input voltage, you will ultimately also see the output dropping. But exactly what happens and when it happens and all of these things is kind of hard to predict, because it is dependent on a bunch of factors, the most important one being how much current you're drawing. So, but the datasheet should give most of that information. And if it doesn't, then, well, get an EK, fire it, connect it to npm power up, where you can actually have a slider on the screen adjusting the output, and hook it up to the load you are interested in evaluating, and see what happens. I think that's the most accurate way to most accurate answer you're going to get, is to actually try.
Great. Then there's someone wondering, what is the maximum current that the nPM1300 can measure? I think we'll change that to deliver.
No, I think measure is okay. Because it is, yeah. So deliver is, we can do both. Deliver is, I think, about 500 milliamps on the unregulated rail, 200 milliamps each on the buck converters, and 50 milliamp each on the LDOs. And if my math is correct, that should be what is that, 250 plus 250, that's about 1 amp. And then the battery can obviously take 800 milliamps of charge current, and we can measure up to those 800 milliamps.
Then we have a question about the model generation for batteries.
Yes.
You mentioned that you only needed one battery. Is there any benefit from, for example, using 3 batteries of the same model to make the model?
That is a good question. I don't know the details well enough. I know that certainly, so that you do 3 measurements at 3 different temperatures. Whether this accommodates more measurements than 3 and can combine those results, I don't know, but I don't think it can. But it's certainly something we should look at. What we found, though, is that batteries are so consistent from one copy to the next that we haven't found the benefit, but that there may be production batches from manufacturers where that is a where that is absolutely a possibility. So it's a great idea. It's not, I don't think it's something we support, but it's something we should definitely look at.
Then there's also a question about if the fuel gauge algorithm can keep track of the battery health.
Yes, there is. If that is in this version or it's something that we're coming out with, I don't. But the ability to first of all adjust to the battery as it is aging, because then the characteristics change quite a bit, and then also look at how the internal resistance is developing. That what happens with the battery as its health decreases is that its capacity is reduced and the internal resistance is increasing. And both of those are measurable, but whether we have a parameter in this version of the fuel gauge that right now that does that, I don't really know, but it's certainly on our roadmap to have that as well.
So here's a little cheeky one. With the nPM1300 coming out, do you anticipate the nPM1100 to be going out of production soon?
No, not at all. The nPM1100 is a totally different product. It is made for really quick development, extremely small volumes, because it takes so little space, and there's still people out there that need only one buck converter and do not want to pay for a second one that they're not using. So absolutely, it's a very different product, both from how it's used and also a much lower cost product. So we do not see a reason to discontinue it.
Great. Here's another one in the also kind of cheeky. As you know, we don't like reading data sheets. So could you tell us what the current consumption is during hibernation and normal power mode?
Yeah, so during hibernation, I think is about 400 nanoamps. And you said the second one was?
Normal power mode.
Normal power mode, yeah, that is depends, because it's a little bit depending on, do you have both the bucks turned on? Do you have an LDO turned on? But it is, I think, in the order of, it's less than a microamp idling. But yeah, and I understand not wanting to read the data sheet, but I do not have those numbers ready from the top of my head. But it's in that range. I know the ship mode current is about 400 nanoamps. The hibernation current, which is ship mode except for a timer running, is a couple of hundred nanoamps higher. It is in that range.
The exact numbers are 370 nanoamps for ship mode and 500 nanoamps for hibernation.
Okay, so I was pretty close.
Pretty close.
Yeah.
Then there was, they also have the same question has a example. How much would it influence the energy consumption when you're using, for instance, a 9160 that has a 6 microamp RTC sleep current?
So if the 9160 is powered, then obviously you get that power on top of everything else. If you turn everything off, so with the 9160, you would have to power that from VSIS, which is the unregulated rail that comes out of the npm 1300. So it depends on, if you shut the whole thing off and you go in hibernation mode, then obviously the 9160 will consume nothing. If it is idling at a few 6 microamps, then you get that on top of what the PMIC is consuming. But the PMIC is consuming less than that, so it shouldn't be much of an error.
Great. Then there was a question asking if we are considering making products that are compatible with super caps.
Yes, we are, but not this one. But we have that on our roadmap. Absolutely.
And then there's a follow-up question to a question on the box. Do I understand correct that it doesn't have 100% duty cycle mode?
I don't think so. 100% duty cycle mode, which means that it wouldn't be switching. So I'm not a DC-DC converter expert, but for the way the DC-DC converter to operate, it has to be switching, and 100% duty cycle, from my understanding of the term, means that it wouldn't be switching, and we don't have that. So, but I can forward that question to our engineers. If you send me an email, I think the email address is in the presentation, Robin, is it? And if not, put it in the chat, and then I'll forward the question to the guy who designed the buck and get the buck converters and get their feedback.
I think the best would be to go through devzone.nordicsemi.com.
Yeah.
Okay, then we have a lot more questions, but I'm trying to filter a little bit. Does it have two-step protection against short circuits?
Two-step protection against short circuit.
For example, can it break the circuit for a few seconds when the current goes up to a certain threshold? Second, the same, but permanently when it goes over a different threshold?
No, there is only one threshold.
Okay. Is there a way to get 5 volts output from this PMIC?
Yes, that would be by adding. So we talked about how this replaces a lot of chips and giving you a lot of extra space. You can use that to get a boost converter from somebody. There are plethora of discrete boost converters in there, and add that to our unregulated rail. So that would mean adding one chip to the system, but hopefully we're taking enough chips off that there is room for that. That's the only way. We have on our roadmap PMICs with a boost converter, but we're not there yet. So this one doesn't have that. And that's the only way to generate 5 volts.
Do we have a longevity program for this product?
That I can't comment on. I'm not sure. This works as with any other. We're using the same. We have the same discontinuation policy on this product that we have on all other Nordic products. So that is a question that somebody else would have to answer. If we were to give some details, I don't have those.
Just to iterate on our current policy on this is that as long as we sell the products, we will continue making them.
That's what I thought. Yeah, and then that policy is no different for this device.
So the answer for the longevity is essentially yes.
Yeah.
And then there's let's have one final question. Does this work with the nRF5 SDK?
Yes.
It does, but we do not recommend starting new projects on the nRF5 SDK. If you're already on nRF5 SDK and want to add nPM1300 PMIC to your design, it's great. But if you are starting a completely new design, please use nRF Connect SDK, which is the latest and greatest and most advanced SDK for wireless products from Nordic Semiconductor. Thank you all for all your questions. I will just make some closing remarks. Sign up for more webinars at nordicsemi.com. If your question wasn't answered, or if you have follow-up questions, or if you need technical hands-on support, go to devzone.nordicsemi.com. And you can also find out more about all our products, especially the nPM1300, if you go to nordicsemi.com. I recommend adding nordicsemi.com/npm1300 to your read list. Thank you, everyone, for watching, and have a great day.